Okay, this is going to be our third video in our electric charge and electric fields module. In this video, we're going to be discussing electric fields, and pretty much everything I'm going to be discussing here maps directly onto section 21.4 from the text. And so let's get into it here. In the previous module, we discussed the effect that one point charge would have on another one, right? We used Coulomb's law. We were able to calculate the forces acting on these points, right? So the influence that one point charge would have on another, and vice versa. Then we were able to also add in additional point charges and see sort of what effect these would all have on each other, right? One thing we didn't discuss was the sort of way in which this influence is transmitted, right? We just have these charged particles sitting there. How is it that one charged particle knows about the existence of the other one? They're not touching each other or anything. So how is this information being transmitted from one charged particle to another one, right? And the way we're going to get at this is by introducing the idea of an electric field. Okay, and an electric field can be a useful way to think about how these electric forces are sort of communicated over these distances, right? So let's say, for example, we have two charged particles. We have particle A and particle B, say, and we're interested in the force that B would experience due to particle A. Okay. Using the concept of an electric field, we could sort of approach this problem as follows, right? So we could consider particle A on its own, right? And then we think about the sort of electric field as this sort of background medium through which A is going to be able to communicate its influence to all other charged particles in its neighborhood, right? And so we place A in this electric field. We see how A changes the electric field. And then when we place B into the electric field, we can see how B reacts to the electric field, which has now been changed by the presence of A. Okay, so we can almost think of this like two people in a pool. The first person jumps in and makes some waves, and then how does the second person know where the first person is? Well, they can see the waves, or they can feel the waves coming toward them, right? And so A is affecting the electric field around it, and B feels this effect on the electric field that A has had. Okay, and this is sort of a abstract sort of discussion here, but we're going to see how this all kind of comes together as we do some calculations in a few minutes here. But before we get into the actual calculations, I wanted to talk a little bit about vector and scalar quantities and fields. Okay. And so what I have here is a sort of mathematical definition for what a scalar function is and what a scalar field is, and this results in, or I mean, a scalar function and a vector function, and this results in a scalar field and a vector field that we're going to see over here. Okay, so let me talk about these for a quick second. So on the top line here we have a scalar function. This is mapping R3 onto R1. And so what are we kind of thinking about here? When we're thinking about a scalar field, temperature is sort of the most common go-to when we think about a scalar field. And so this would be, let's say for example we have some room. Okay, so we're sitting in a room and we want to find the temperature at different points in the room. They're going to be slightly different, at some point on the ceiling close to a heating vent versus some point on the floor far from the heating vent or whatever, right? So let's say this is our function that's going to give us our temperature, right? So this is our scalar function here. And we're going to feed it position vectors, right? So let's say we have some room. Maybe I'll draw a little bit of a room here. I don't have a lot of space, but maybe that's not great. How about like this, let's say? So we have some room. Let's call this point here our origin. And so if I want to know the temperature at some point in the room, I have some position vector, right? I'm going to call that R. So I feed this position vector into our scalar function. It takes in R3 information, right? So it has an x coordinate, a y coordinate, and a z coordinate, and out it pops the temperature at that point. But it's just popping out a single number, right? It's popping out just say whatever for the room I'm sitting in now. Maybe it's like 21 degrees in here, so it'll pop out 21 degrees Celsius at that point. So that's a scalar function, and the result is a scalar field. This scalar field is basically giving me a temperature value for every point in the room, right? For any point I may pick in the room, for any point that I choose a position vector to point to, I can pull out some temperature in the room, right? Okay, so that's our example for our scalar field. But what's going on with the vector function and the vector field? So this is our vector function. It's mapping R3 onto R3. So again, I'm feeding it position vectors, but instead of it giving me a temperature back, a thing with just magnitude, it's going to feed back something with magnitude and direction. Okay, so it's going to give me back a vector quantity, right? And that's why we call this a vector field. So a good example of this is gravity, and I've kind of pre-drawn it here, but it's not super easy to see. So maybe I'll draw it a little bit larger here, and we'll work with it here. Okay, so imagine that, for example, I have the Earth here. So this is like the surface of the Earth. I'm just drawing like a quarter sort of slice of it. This is the surface of the Earth here. We can imagine this is our origin of coordinates, and I want to know what the acceleration due to gravity is going to be at some point here just above the surface of the Earth. This is my position vector r, and so at this point, this is going to have some value. We're going to have some value, and the magnitude of it is going to be 9.8 meters per second squared, right? So we know that at or close to the surface of the Earth, we have about an acceleration of 9.8 meters per second squared, but it's also going to have a direction, right? We're going to have this thing pointing downward, so we're going to end up with a direction of minus j hat, right? Let's say we're using polar coordinates, and we're aiming downward here, right? So at this point we have a g, but now our g is not just a scalar, it's a vector, right? So we have our magnitude and our direction. And anywhere around the Earth I can pick a point. Let's say I picked a point here. This would be my position vector r, and this point would again have a direction. So our j hat would point in that direction now, and it would also have a magnitude. So this is sort of all just a long-winded way of saying that our vector function here is mapping R3 onto R3, and this resulting R3 is giving us a vector field. I can choose any point anywhere in the vicinity of our Earth here, and I can draw a position vector out to it, and it'll give me back a vector which will give me the magnitude of the gravitational acceleration there and the direction of it, okay? And that's the difference between a scalar field and a vector field. We're going to be working with the electric field, which is a vector field. So at every point we need to be getting back a magnitude and a direction. Okay, and we're gonna develop this idea of an electric field in sort of direct analogy to the way that we talked about the gravitational field a moment ago, right? So again, as I said above, near the Earth's surface we have a gravitational acceleration given by this expression here. And we know from our earlier work that we can write the force of gravity as being the gravitational acceleration times the mass of whatever it is the object we're talking about is, right? And this is really just Newton's second law written in terms of gravity, right? But we can kind of rearrange this to isolate our gravitational acceleration, right? We can just put g on its own and divide our m naught through. And so in this case, what is m naught? Well, m naught's really a point mass. Really, we want it to be a point mass so that it's small enough so that the gravitational acceleration is not drastically different at different points on the object, right? So we're thinking of a point mass, and we can interpret this g as a force per unit mass, right? So usually we think about it as an acceleration, but it's also a force per unit mass, because if we divide a force if we divide the mass out of a force, we end up back with an acceleration, right? So it is a force per unit mass. So we can now develop this idea of an electric field in much the same way that we sort of discussed this already familiar idea of the gravitational field, right? So what are we going to do here? We're going to start by instead of having our test mass, our m naught, we're now going to have a test charge, which we're going to call q naught. Okay, that's our q naught here. And so we replace m naught with q naught, and what are the sort of restrictions on q naught? Well, q naught, we by convention choose to make q naught positive. So q naught is a positive charge. It needs to be point-like. Okay, so we don't want it to be like some large charge distribution. It's a single point that has some charge. If it was a large charge distribution, we would run into problems because our electric field might be different at different points, right? And so if the charge distribution is large at different points in that charge distribution, the electric field is different, and so it's experiencing different electric forces at different points, and it becomes much more complicated to work with, right? So we need to make sure that our q naught is positive, that our q naught is point-like, and in general, we want a small q naught because we're talking about a test charge here. We don't want it to sort of dominate the problem. It's just a test charge to test what the electric field is doing at that point. Okay. And so if we do that and place our test charge at some point p in space, then we can write the electric field in very much the same way that we wrote our gravitational acceleration, which we now think about as a force per unit mass. We can now write down our electric field. So this used to be our gravitational field. This is now our electric field. This used to be the force experienced by m naught, but now it's the force experienced by q naught due to the electric field. And this used to be our m naught. This is now our q naught. This is our test charge. Okay, this is the sort of magnitude of the test charge. Okay, and so if we look at this, we can see that the SI units for our electric field have to work out to be newtons over coulombs, right? Newtons per coulomb, because our force is in newtons and our test charge comes in coulombs. We're later going to see that we can actually write this in terms of volts per meter, but for now it's going to be more useful for us to work in terms of newtons per coulomb. Okay, so when we think about an electric field, we're going to think about, so we place some sort of charge in the electric field, and the force that it experiences is going to be scaled by how strong that charge is, right? So we have newtons per coulomb. Okay. So we can rearrange equation 2 here and write it as we see here in equation 3. And then we don't necessarily have to be dealing with a test charge. Once we know the electric field, we can place any charge in that electric field and see what the electric force that charge experiences due to the electric field using this equation 3 that we have here, right? So this will be the force on our charge Q is going to be equal to the magnitude of charge Q times the electric field, and this is a vector quantity, so we always need to be careful that we're dealing with vectors here, right? The force experienced will have a magnitude and direction, but so does our electric field, and so it all kind of works out. Okay. So I make a point of saying it one more time here. We want to be careful to only apply this to point charges. Okay, so we need to be careful that when we're putting a charge in an electric field, this charge needs to be a point charge. Otherwise, this isn't going to work, and it's going to be more complicated to calculate, right? So we put a point charge in an electric field. We can calculate the force experienced by that point charge using equation 3 here. Okay, so we're going to slightly change gears here, and we're going to start off by calculating the electric field of a point charge, right? So we're putting a point charge at some position, and we're calculating the electric field at another point P, some distance away from our source point, right? So we're putting this charge Q is going to be our source point, and we're going to be calculating the electric field at some point P further away. Okay, and so the way we're going to do this is we're going to start off that we're going to look at for some source point Q at some field point P, defined by a position vector that's going to draw a line from our source point Q out to that point P, and we're going to call this position vector R. We want to calculate the magnitude of the electric force experienced by a test charge at that point. Okay, so that was a bit of a mouthful, but basically what we're going to end up doing is we're going to end up using this equation that we see here, equation 4, which we worked with in the previous video. We're going to use this to calculate for the situation that I have drawn down here. Okay, so we have our source point Q located over here. That's going to be our sort of origin of coordinates in this case. And then at some point P out here, where we put a test charge Q naught, we want to calculate what the electric force experienced by Q naught at that point is, right? And so, excuse me. And so we know how to calculate that. We did basically this in the previous video, right? And so we can do that calculation, and we can sort of see how that's going to work out, right? So we have our source point here. We have our position vector R here. We know we can get the unit vector R hat from our position vector R, and we can calculate what F will be at point P from that. If our source point is positive, we can see that F will point away, right? And sort of why is that? Because we're using a test charge that's positive, so we're going to have positive charge here, positive charge here. There's going to be a net repulsive force, and we can see that that's going to be in this direction. If our source point is negative, though, let me just pause the video for 1 second to clear my throat. All right, sorry about that. Okay, so we can see that if our source point is negative here, and again our test point, our test charge is going to be positive, we're going to have a net attractive force, and we're going to have this force acting in the negative R hat direction, right? And so that's great. So we can do this calculation. We can see by inspection that we're going to end up with an expression that looks like this, right? So we have this same expression above here, except what's happened, we now have a direction added in. We know that F is going to point in the direction of R hat, and it'll either point negative or positive R hat, and that's fine because that's going to be determined by the sign on our Q here, right? So it'll either point negative or positive R hat. If Q comes in as a positive source charge, then that's fine, it'll point in the positive R hat direction. If Q comes in as a negative source charge, then it'll point in the negative R hat direction, right? And so if we sort of play this out, and we have our source point, so I've drawn this in sort of two different cases here. Here we have a positive source point, and we can place our test charge at any point around our positive source point, and we see that we get a resulting force vector that's sort of being experienced by that test charge, and it'll always point away because that's the direction of R hat at that point. It'll always point away from our test charge, and the exact opposite is true for a negative test charge, right? If we have a negative test charge sitting at our origin here, and we place a positive test charge, or I should say, this is a negative source charge, right? I'm not sure if I said source or point charge before, but this is our negative source charge, and if I place a positive test charge at any of these points here, we can see that our force vector points toward our source point because we have an attractive force, right? So that's great. We can calculate the force at all these points, but if we can calculate the force at all these points, we can go back to our definition here, equation 2, our definition of the electric field, and we can simply substitute in our what did I call it, equation 5 here, and if we substitute in for our vector F into equation 2, we end up with this equation here. The Q naught, our test charge, divides out, and we're simply left with this expression here, which I've boxed over here. This is going to be a pretty useful equation for us, so we want to make sure we keep 7 sort of in our minds all the time. This is our equation for the electric field of a point charge. And so we end up with K, which is that constant that we talked about before. This is 9 times 10 to the 9 with some units that we can talk about. Then we have our source charge. This is not our test charge. We want to make sure that we keep in mind this is our source charge. And this is going to be this R is the the magnitude of our position vector pointing to whatever point we're interested in looking at, right? And this is our r hat. This is the direction of our position vector pointing to whatever point we're looking at, right? And we can keep in mind that we can calculate both r and r hat. We would calculate r hat from this expression here, and we need to get the magnitude of our vector r to be able to get r, right? Okay, so we've kind of talked a little bit about the theory of sort of developing this idea of an electric field. Now we can do some examples. Okay, so I have two examples in mind here. We'll try to get to them kind of quickly here. So I have numbers worked out over here. Hopefully it all works out. Okay, so we have a point charge, Q equals minus 45 nanocoulombs, placed at a position 1 meter in the plane here. So this is our XY plane, and we can imagine we're plopping point charges down on it. So we have our source charge at 1 meter in the plane here, and then we want to find the electric field at a point, and I'm going to call this point P here on the diagram, at 2 meters, 3 meters in the plane. Okay, so x equals 2 meters and y equals 3 meters. And so we can see from the diagram sort of what's going on here. I've drawn it maybe a little smaller than I should have, but we can kind of work with it as is. Okay, and so we have our source point here sitting at 1, 1, and just our P, the point that we're interested in, up here at 2, 3. Okay, and so R is the position vector, which is going to connect our source point and the point that we're interested in. So R connects the point Q here and the point P. So the first thing we need to do really what we want to do is we want to find R. We don't know what R is. We know what these points are, but we don't yet know what R is exactly. And with that, we also want to find R and r hat. So we want to find the vector r, we want to find the magnitude r, and we also want to find the position vector r. Right? And I've drawn in the position vector here. This is what the position vector would be. And the magnitude r would just be the sort of length of our vector r. So what's the easiest way to do this? Well, the easiest way to do this is probably by thinking about what the position vectors of our source point and our P, the point that we're interested in, are, right? So let's maybe write those out first. So the way I would do this is I would write RQ. So what is RQ? So RQ is this vector that I've drawn in here. This would be RQ as a vector, and it's basically the vector that points from the origin to the source point that we're interested in. So what is that? Well, that's going to end up being 1, I'll write in the ones in this case, 1 I hat plus 1 j hat meters, right? So this would be the vector that points to 1, 1, right? Simple enough. And then I would define also a vector RP, and this RP would point from the origin to the point P that we're interested in looking at. And what would that be in this case? Well, that would be 2 I hat plus 3 j hat meters, right? Because we're dealing with meters here. Okay. And so now let's remember some of the things that we should know about vector addition and vector subtraction, right? So we can see that sort of by adding these vectors tail to head, that it must be true that RQ plus R equals RP, right? We can see that if we add RQ and R, we're going to end up with RP, right? Adding tail to head. Well, this means that if we shift our RQ over, we're simply going to end up with R must be equal to RP minus RQ, right? And this is a very easy way for us to get R. If we just do that vector subtraction, we basically sub in RP here, RQ here, and then we simply subtract term by term, right? So we end up with or maybe I'll write it out in full since it's the first time we're doing this. We're going to end up with 2 I hat plus 3 j hat minus I hat plus j hat, right? I won't include the ones anymore here. And so what does this give us? Well, this gives us an R equal to I hat plus 2 j hat, right? And this is going to be in meters. Okay, so this is one result that we want. We need r. And so what else do we want? We also want the magnitude of this vector. So we want the magnitude r. And how do we find that? Well, we know that we can get the magnitude r by looking at the components of our vector r. This is going to be rx squared plus ry squared, and then take the square root of all of it. So this is going to end up giving us 1 squared plus 2 squared, square rooted, which is really just the square root of 5. And I'm just going to leave it as the square root of 5. Again, remember, this is going to be in meters, okay? And finally, we also want r hat, right? Put a comma here. So we know that we can calculate r hat. We talked about this a couple of times now. We can calculate r hat by taking our vector r and dividing it by the magnitude of that vector, right? And so if we do that, we have our, maybe I'll just write it like this here. We'll have 1 over square root 5. This is our dividing out of the magnitude, and it's just times the vector r, which is basically just I hat plus 2j hat. Okay. Okay, so this is our unit vector, and again, this has no dimensions, right? Maybe I shouldn't solid box that. I'll dotted box it. Okay, and this is r. These are the 3 values that we wanted. Okay, and so now we're kind of ready to calculate what the electric field at the point P is. Let's write down the expression that we want to work with. So we just saw above that we define our electric field in these terms. So this is k q over our magnitude r squared, and it points in the r hat direction, right? And we can just straight substitute in what these values are. We remember, and I'm not going to put in units here because it's going to clutter the calculation, but obviously some of these things would have units, and in the end we know this is going to work out to be in newtons per coulomb. But if ever you're having problems with looking at an example, go back through, put in the units, and make sure that your units are working out, right? And so what do we have here? We're going to have 9.9. Oops, nope. That's not 9.9. That's 9 times 10 to the 9. And then in the top, we're told that we have 45 nanocoulombs, right? Negative 45 nanocoulombs. So we're going to have negative 45 times 10 to the 9 over square root 5 squared. And this is pointing in the r hat direction, which we just said is this value right here, I hat plus 2j hat, right? And so we can clean this up. I won't do the full cleanup here, but basically you can kind of see it right away. This basement's going to end up being a 5. These two 10 to the power 9s are going to cancel, so 45 divided by 5 is going to give us 9, so we're going to have a negative 9 on top, times 9 is going to give us a negative 91. Yeah, so basically here I'll do one more step. So we're going to end up with a negative, sorry, I meant 81. So negative 81 over root 5 times I hat plus 2j hat, right? And this is going to be in newtons per coulomb, right? And so if we finished this calculation, clean that up a little bit, and I'm going to move the minus sign inside so we get a better sense for what direction this thing is pointing in, we would end up with an E that would look like this. It'll be 36.2 negative I hat negative 2j hat newtons per coulomb. Okay, and that is the electric field at the point P. That's what we're looking for in this problem. I'm just going to pause for a second to save this PDF so I don't lose it. Okay, and we can keep going. So that was our first example. Maybe I'll make a quick additional note up here. So up here we talked about the sort of direction that the test charge would feel depending on sort of what source charge we have here, right? So we had a positive source charge here, and all of the forces experienced by the test charge were always away, and it was sort of the opposite case for our negative source point here, right? But we also now can think about the electric field. So now that we've sort of discussed the electric field and we looked at an example, what would the electric field look like around these different source charges, right? And it's kind of the way you would sort of expect it to look. Maybe I'll put in a line here. And so what would we expect to see? So let's say we had So we had some source charge here. Let's say it was a negative source charge. Well, we would expect that our electric field at every point around it would point like this, right? And that's actually what we do find if we calculated this for basically for all these points around this, we would find that our electric field looks like that around a negative source charge. And the exact opposite would be true for a positive one. We would find the electric field lines all going away from our positive charge, right? So this would be our electric field around a positive source charge. Okay, and they have some nice sort of drawings of this in, or nice diagrams, I should say, of this in the textbook if you want to look at it a little bit further. But we're going to move on to one more example here. We're going to take a look at example 21.7 from the text here. I have it copied into the notes here directly. I think I have some numbers worked out for it here. And I do. Okay, so let's give the problem a read through here. So maybe I'll scroll down a little bit so we have the diagram too. Okay, that looks pretty good. So when the terminals of a battery are connected to two parallel conducting plates with a small gap between them, the resulting charge on the plates produces a nearly uniform electric field E between the plates. Okay, so we can kind of see that here. We can see that we have our battery. We've connected the negative terminal to the top plate and the positive terminal to the bottom plate. And so we have negative charge building up on the top plate, positive charge building up on the bottom plate, and it sets up this nice uniform electric field that we have here. We see they've labeled it with these sort of purple lines and this E here, right? And so that's great. We have a nice uniform electric field. So everywhere between these plates, the field is basically the same. Okay. And it mentions that in the next section we'll see how this works. That's great. We'll take a look at that in a little bit. But for now, we want to do some calculations with this. So let's continue with the problem. If the plates are 1 centimeter apart and they're connected to a 100-volt battery, as shown in this figure here, the field is vertically upward and has a magnitude of 1 times 10 to the 4 newtons per coulomb. And now we want to find in part A, we want to find if an electron with a charge given here, negative 1.6 times 10 to the minus 9 coulombs, that has a mass of 9.11 times 10 to the minus 31 kilograms, is released from the upper plate, what is its acceleration? So that's the first question. Then we want to know what the speed and kinetic energy of this particle are as it travels the sort of 1 centimeter down, right? So let's take a look at this here, and we'll sort of do the calculation. I have a spot for the solution down here, but I guess I could start it up here. Okay, so what are we sort of looking at here? Well, we're looking for an acceleration, right? That's the first thing that we're wanting to find, right? In part A, if it's released, what is its acceleration, right? So part A, we're looking for the acceleration. Let's start off with the expression that we wrote down for the electric force experienced by a charge in an electric field, right? This was the equation that we wrote down up here. What was it? It was equation 3 here, right? Okay, so we'll write down equation 3, Q, E. And we also know Newton's second law tells us that F equals ma, right? This will be a vector also. And so we can rearrange F equals ma to give us this expression here. And at that point I can sub in for F from our equation 3 from above, and this is going to give us A is equal to Q over M times our electric field, right? And so we can sort of simplify this a lot. We know that since the electric field is uniform and it's pointing straight up and down, we know the only acceleration that we're going to see is in the y direction. So we're going to have AY. This is going to be equal to Q over M times the magnitude of our electric field times the direction, which I would normally write in as E hat here. But in this case, we know that E hat is pointing is pointing in the j hat direction, right? So it's just in the j hat direction, And we don't need to include that j hat because we're talking about the magnitude of our acceleration in the y direction. So we know it's in the y direction. So that's basically all that we need to write there. And basically now it's just a matter of substituting in some numbers, right? So what's q here? Well, q is minus e. It's the charge on our electron. And so we end up with this expression here, and we're given all these numbers in the problem. We can sub in this minus e, we can sub in for m, and the electric field is also given to us. So I'll write that out here. We end up with minus 1.6 times 10 to the minus 9 over our mass, which was 9.11 times 10 to the minus 31. And so yeah, so this would be in coulombs, this would be in kilograms, and our electric field is 1 times 10 to the 4 newtons per coulomb, right? So we multiply through by coulombs, we end up with only newtons on top, and then we divide through by kilograms. We know that a newton is a kilogram meter per second squared, and so we end up with meters per second squared, which is exactly what we would expect because we're expecting an acceleration here, right? So if we do that calculation, we end up finding that AY is minus 1.76 times 10 to the 15 meters per second squared. Okay, and minus because it's pointing downwards, right? So we've picked a positive upward direction, right? Okay, so in part B, I believe we're looking for the velocity that this charge is going to have when it gets to the bottom here. So I'm going to set this bottom part of the top plate as my y equals 0. Okay, so this is y equals 0 here, and then we can sort of do this calculation. Maybe I'll do it down here. I'm going to label this B, and so we're looking for the velocity as the electron slams into the bottom plate, and we can simply do this using the kinematic equations we would have sort of seen back in 111, right? Or maybe really back in high school physics, you would have probably seen this as well. And so we've set y equals 0 at bot of top plate. Okay, so we've set our y equals 0 at the bottom of the top plate, and then we can simply use, so from kinematics, we know that v squared is equal to v naught squared plus 2a y minus y naught. So we should all sort of remember that one from whenever we worked did work in kinematics. And so we can sort of simplify this because we know that initially there was no velocity, and we set our y0 to 0, and so this is also 0, and so this simplifies down to v squared is equal to 2ay, and we can isolate our v. So our v is going to be equal to plus or minus, and remember, we're taking the square root of both sides, so it is going to be plus or minus the square root of 2ay, right? And so we know that our velocity is going to be negative, so we're going to end up choosing the negative direction here. And so we have a v equal to minus the square root, and I can substitute in numbers now, so this is going to be 2. The acceleration from above we found was minus 1.76 times 10 to the 15 meters per second squared, right? And the y that we cover, well, we're covering 1 centimeter, right? This is 1 centimeter of distance between these two plates, but we have to be careful to change that into meters. That's going to be 0.01, and we also have to be careful that y is in the negative direction, right? We're covering a distance downward of 1 centimeter, and so we end up with minus 0.01 here. And if we do that calculation, we're going to end up with a positive number, right? We have a positive number inside the square root. We have 2 negative numbers, so this is going to give us a positive number. If you do the full calculation, you're going to end up finding that v is equal to, and again we chose this negative for our square root. You're going to find v is equal to minus 5.9 times 10 to the 6 meters per second. Okay, and that's our answer for part B. I believe in part C we were looking at the kinetic energy that this particle is going to have as it slams into the bottom plate. And so we just remember our expression for kinetic energy, That's simply 1/2 mv squared. And we just calculated what v was. We were told what m was, and so we can pretty easily do this calculation, right? We end up with 1/2. M was this value here. And we need a v squared, so that's going to be squared. And if you do the calculation, you're going to find that the kinetic energy is equal to 1.6 times 10 to the minus 17 joules. Okay, and that's the answer to part C. Okay, so that was our first look at electric fields. We're going to do some more electric field calculations in the next video, and I will see you guys there.